13. We started talking about solutions last time. And remember that a solution is really made up of two parts. It is the solute, which is our smaller part. And we also have our solvent, which is the larger part of the solution. Remember that those together pretty much makes a solution, and those are the guys that get the aqueous symbol next to them. We talked really about as well solubility and the idea of like dissolves like. And remember that pretty much a majority of the reasons why certain things are able to be sort of soluble in each other and other things are insoluble in each other has to do with those sort of intermolecular forces we were talking about. And remember that there is basically hydrogen bonding. There's dipole-dipole interaction. And there's dispersion forces. And each of these are ways that one molecule basically reacts with itself or other molecules. Remember that hydrogen bonding, you need a bond between hydrogen and nitrogen, oxygen, or fluorine. And those are really polar molecules that basically has that bond available to them. Will be able to hydrogen bond. And if you remember, that's pretty much a pretty strong interaction. That's really the strongest. Dipole-dipole is where we have our polar molecules, just like we do with hydrogen bonding, which really is sort of a category of dipole-dipole interaction. But dipole-dipole is really for our polar guys that don't have the ability to hydrogen bond. So those ones that really cannot hydrogen bond. But they are still polar molecules are the ones that will do this. And it is also pretty relatively strong. Really the weakest out of all of them that we talked about is really our dispersion forces. And these are basically our non-polar guys. If you remember, sort of our non-polar molecules basically will share our electrons equally. And because of that, they do rely upon these dispersion forces, which basically needs something to occur. So either the electrons in their own molecule need to kind of go one way or the other to create a temporary sort of charge, or they can be induced by something that does have a charge, something that's positive or negative comes near it. It kind of makes their electrons kind of go one way or the other. But these are really weak sort of interactions because they're dependent on that interaction to occur. But as soon as that interaction basically goes away, so will the ability of them to really kind of bind to one another. So this is definitely the weakest out of all of them. And really what makes something sort of soluble in each other, as we talked about, is that idea that, you know, if we have a molecule that's able to hydrogen bond with itself, and it comes across either another molecule that also has the ability to hydrogen bond, that will allow them to really interact well with each other. They both will be using pretty much their main way of interacting, and they typically will be soluble with each other. If we have something, again, that can hydrogen bond, but comes across something that really does rely upon pretty much just dispersion forces, although, as we've talked about a couple of times, that, you know, in the sort of the short period of time, they can sort of interact with each other. They're not going to have a way to keep that interaction going for over the long period of time, and they really will sort of separate out from each other. Again, like our sort of oil and water sort of example. Again, they will very much sort of separate out from one another. So what this means is, in terms of sort of solubility, you know, if we have things that are typically soluble are ionic things and polar things, polar and polar guys. And as we talked about, sometimes overlooked by a lot of people is actually nonpolar and nonpolar things. Again, they will be soluble in each other. As you might have saw in the experiment the other day, you know, if you have two liquids that are nonpolar and nonpolar and you mix them together, like your heptane and your hexane, they all should have mixed and became one liquid. When you did like methanol and hexane or heptane or whichever one you put together with that one, you probably saw a couple of different layers because the methanol wants to do hydrogen bonding and the other one wants to do dispersion forces, so they probably layered out. Same thing with your solids, right? You took something like potassium permanganate, should have dissolved in water because it was polar and ionic. But when you put it in with hexane, which is non-polar, you should have saw it not dissolve really, the solid. And opposite there, when you took your iodine out of the fume hood there, you should have saw it kind of dissolve in the hexane and not so much in the water. Again, when you run across polar and non-polar together, they really are insoluble in each other. So that is basically what we got going on this side, is that polar, non-polar. We then talked about sort of concentrations or ways to also describe solutions. Remember, solutions can be described as being saturated, which means it has the maximum amount of solute that will dissolve at a given temperature. You could have an unsaturated solution, which means you pretty much have not hit that point there. So you can continue to dissolve your solute and it will continue to dissolve until you pretty much hit a saturated solution. And then hopefully, as you saw there in demo A there of the last experiment, you could have something like a supersaturated solution, which is basically a solution that has way too much solute sort of dissolved in it. And just by adding one crystal, like you probably did in the lab, I assume, right? And all that solid basically came out of solution. Or again, if you tapped it too hard, it might have came out of solution when they did that. We got into concentrations, and there's a few percent concentrations we talked about. We had percent mass to mass, which is our mass of our solute divided by the mass of the solution times 100%. We also had percent volume to volume, which is the volume of solute divided by the volume of solution times 100%. And there was also percent mass to volume, which is the mass of the solute over the volume of solution times 100%. Remember, out of all these, really that kind of percent mass to mass, it's really important. The bottom part of that, really, they very often will kind of split up the solute and the solvent in those type of questions. So once again, as we talked about, you do want to make sure that you actually get the mass of the solution and not just the solvent, which again is a common sort of mistake that's made. We lastly sort of finished up with the idea of molarity, which is big M, which is moles of solute over liters of solution. Remember, you could think of this sort of as a formula. You could solve for liters, which would be moles divided by molarity, or you could solve for moles, which would be liters times molarity. Remember that you do need to make sure that the volume's in liters when you are using it with molarity. And as we talked about, you pretty much want to get rid of that big M when you're doing the calculation. So if you had a 3.5 molar barium chloride solution, that would mean 3.5 moles of barium chloride per liter. And you can also use it like a conversion factor. You could flip it on its head there and go liters up on top and moles on the bottom. The advantage of, again, doing it this way is you can see both of those units like we talked about. I can't tell you how many people come up to me and go, I have this many moles when they point to the big M, and again, either have no idea that there's volume associated with it, or again, where the volume should be. We also talked about the relationship between the concentration and individual ions. So remember, you could kind of do it like a stoichiometry sort of relationship. If the thing breaks apart into 2 ions, then it's basically twice the concentration because you have twice as many of those ions floating around. Any questions on any of that stuff I think we talked about last time? Okay, then let us continue on here. So speaking of ions, why don't you do this problem here? So for these two separate solutions, what is the concentration of each of the ions? So for this guy, we're looking for the sodium ion and the sulfate. And for this guy, the potassium and the chromate. So what would be the ion in each of those, or the concentration of each of those ions in each of these solutions? They're two separate solutions. We really want to think about, what this thing breaks apart into when it's in solution. So when we do have something like sodium sulfate here, when it is in solution, it was a strong electrolyte, so it will break apart into a couple of sodium ions plus a sulfate. So really, when you have a solution like this guy, that's really what you have floating around is you got some sodium ions, you got some sulfate ions. Remember, the whole unit is not together anymore, right? Because it's a strong electrolyte, so it will 100% break apart. So we really could take a sort of stoichiometry approach to concentration, and it works out really well. And it's sort of a faster way of doing the calculation and figuring it out. So really, we could just do like the whole thing here. There's one of the whole things, and we get basically two of the sodium ions. So how that works for the concentration is we would take the concentration and multiply it by 2. And for the sodium ions in solution, it would be 2.4 molar of sodium ions. We could do the same thing for the sulfate, basically just like a mole to mole sort of relationship. That's a 1-to-1 relationship here. That means basically we take 1 times the 1.2 molar, and we would get 1.2 molar of the sulfate ions that are floating around there. Remember that they're not additive, sort of the ions concentrations, but they are sort of proportional wise what you get. Basically, every time you go for a swim there, you're going to get twice as much sodium as you are sulfate. So the concentration of the sodium ions in this case would be twice as much as what you would have for your sulfate. A reminder that if you did the sort of longer version of this calculation, and I'll just do it for the sodium here to show you really how we get there one more time, is we would take the original concentration of the that's what the big M stands for, right? And you basically just do a mole to mole relationship, 1 mole to 2 mole from the equation. So that would do a 1 mole of the whole thing, gives you 2 moles of the sodium ions. The moles of the whole thing cancel, and you end up with 2.40 moles of sodium ions per liter. That is essentially where the 2 comes from. It's really the stoichiometry part of it, the mole to mole relationship. So you can just do the quick way there and get to the answer, or this is really the dimensional analysis way as to how you get there. Obviously, the sulfate would be the exact same thing, except that why we multiplied it by 1. Any question? Understand the long version, just in case you ever need to do it, but the short version is really good, and it sort of helps you out a lot quicker. It's to stuff with it, so it's okay if you do sort of the short version, but you do need to show something maybe like 2 times the concentration or something like that. So I understand I know how to get that number. Other questions on that? Okay, so let's take a look at the other guy, which was in this case K2CrO4. Once again, when this breaks apart, we will get a couple of potassiums and a chromate here. And we'll do the same sort of approach here, since this guy is 0.75 molar for the whole thing. Once again, here for the potassium, it is a 1-to-2 relationship. So we'll take 2 times 0.75 molar, should give us a concentration of 1.5 molar for our potassium ions. And once again, here our whole thing to just the chromate is a 1-to-1 relationship. So we'll take 1 times 0.75 molar, gets us 0.75 molar of our chromate here, chromate. Any question on either two? So you will sometimes in sort of and molarity, and even with solution, which we'll talk about. Sometimes they do kind of focus in on just a single ion or something like that in a solution. So this is a way to go from the whole thing to just the individual ions. Obviously, you do not need to do this on every molarity question unless it specifically involves just sort of an individual ion. All right, so let's try another example here for molarity, which actually does do this. So we want to know how many moles of the sodium ions are present in 42.0 milliliters of 0.35 molar sodium chloride. Okay, so again, if you're not sure where to start, clearly there's molarity involved. So you can think about the sort of molarity formula, which is moles per liter. We are obviously given a molarity and we have a volume, although it's not in liters, but we can easily get it to liters. So obviously here, we're probably going to use this equation and solve for moles, which is ultimately what we're looking for here. And moles in this case would be liters times the molarity. In this case, though, we are interested in just the sodium ions. So we do have a couple conversions we need to kind of do along the way here. So always when we're using molarity and volume, you got to get it into liters. So a reminder that there are 1,000 milliliters in a liter, which essentially you'll just move the decimal point over 3 places to the left. Give us liters. Once again, here, we're not necessarily in this particular problem interested in the whole thing. We're just interested in the sodium ions part of it. So we can apply what we just were talking about in the previous problem, that in the sodium chloride, it will break apart into a sodium ion. If the whole guy's concentration is 0.35 molar, which means the concentration here of sodium ions, right? By just so you know as well, right, the chloride ions here would also be in this case 0.35 molar, but you don't need it for this problem. So at this point, we really have now the two things that we need here to solve for moles. Once again, I'm going to get rid of my big M, and that means I have 0.350 moles per liter of these sodium ions, and I'm going to use it more dimensional analysis so I can see everybody's units. So we'll take our volume, 0.042 liters. We're going to use our molarity like a conversion factor with 0.350 moles of sodium ions per liter. Liters will cancel and will get us 0.0147 moles of the sodium ion. Any questions on that calculation? Now, alternative to this, you could have just used the sodium chloride like all together, and then at the end got the sodium chloride and did a mole to mole relationship to get to the, obviously in this case. So you didn't necessarily have to go right into the ions at the front, but you could have converted at the end. But somewhere along the way, you need to relate the sodium chloride to just the sodium ion. Yes. On that one. Okay. So let's take a look at another one here. We're looking for what is the mass in grams of sodium nitrate that's needed to make 2.5 liters of a 0.15 molar sodium nitrate solution. Sodium 2299 on the periodic table, nitrogen 1401, and our oxygen still 16. All right, so take a couple of minutes. We're looking for how many grams here, kind of similar to the last part of the experiment the other day. Okay, so let's take a look. And again, if you're not really sort of sure where to go, you can pull out the information. Again, we do see molarity. So we should think about our molarity equation. And once again, if we kind of check off what they gave us, we obviously do have the molarity given to us. We also do have the volume given to us. So it would make sense, obviously, in this case, to solve for moles. And that does make sense because we know how to easily go from moles to grams, which is what we're looking for. And that would obviously be the molar mass to do that. So that's where we'll start. So once again, I'm going to pull this molarity into 0.15 moles per liter of sodium nitrate so I can see all the units. In this case, our volume is already in liters, so we don't need to convert it. So we'll just do our 2.5 liters. We're going to multiply it by the molar, which is 0.15 moles per liter of our sodium nitrate. The liters here will cancel, and that will give us 2.5 times 0.15, 375 moles of sodium nitrate. At this point, we got our moles. We can now go into grams, but we do need to calculate the molar mass of sodium nitrate. So that is 1 sodium at 2299, our nitrogen at 1401, and we have 3 oxygens at 16 in this case. That's going to give us 85 grams per mole as the molar mass. We're going to use as a conversion factor, so 0.375 grams, not grams, moles. Again. Moles here of our sodium nitrate. We will multiply it by the molar mass, 85 grams up on top, and a mole on the bottom. The moles cancel, and that gets us times an 85, 31.9 grams of sodium nitrate. Any questions on that calculation? So basically, if we wanted to make the solution, you would weigh out about 31.9 grams of it, take some water, dissolve it, and fill it up maybe with a volumetric flask or some other measuring device with enough water to get a total volume of 2.5 liters. Give it a good mixy, a little shaky, and you should have a 0.15 molar solution sitting in front of you. Any questions on molarity here? So next thing we're gonna talk about is dilution, and oftentimes a lot of solutions do come as more concentrated solutions, as we talked about before, and a lot of times we will use them in a more dilute fashion like we do see in the lab. And when we do a dilution, really the only thing that we're doing is really adding more solvent. So it's really just adding more solvent. And as we talked about, a lot of times the solvent is water, but it doesn't always have to be water, but in a lot of cases it really is water. And the reason we do a dilution is to really create a concentrated solution than what we started with. And the way that works is we could actually look at the molarity equation, which is really our moles of solute over liters of solution. And remember that the solution is both the solute plus the solvent, which means when we actually add more solvent or water, the only thing we're changing is that number right there, which makes the bottom number larger, and that makes the molarity smaller, right? So that is why the molarity goes down, because we're really adding more solvent, which is more solution, and that gives us a lower concentration than what we started with. Now, it's important to remember that it really is the solute, as we might have talked about last time, that is what is reacting. So it's whatever's floating around as the solute is really what's there that does, any type of chemical reaction that might occur. And in terms of the solute, as you can see from what I just circled, the solute is actually not changing. Even when you do a dilution, we didn't add more solute, which means neither one of those things really change. So when you do a dilution, your moles of your solute before and after dilution still remains the same, because frankly, all you're doing is sort of adding water in most cases. A very common way we could do a dilution is you could use a volumetric flask, kind of like what you used the other day. And you could add some water to begin with, or more concentrated solution in there, and then obviously top it off to the water. Nobody went over the line, did they? When you were making it the other day. But you do want to go obviously to the line. So that's where you should go. As that's a volumetric flask, which means that is the correct volume. Why should you not, why if you go over the line, should you not just pour it out at that point? Yeah, because the solute at that point is dissolved, right? If it was a solid, it's dissolved, or if it's a liquid like that. So when you would pour it out to bring it back to the line, you technically dumped out some of your solute, which means your molarity would not be the correct molarity at that point. So sometimes when people use volumetric flasks like that and they go over, they go, I just like pour it out back to the line. And it does make a difference because you would lose obviously some of your solute that was in there. As we fill it to the line, we obviously end up with our little less concentrated solution at that point. So there is a formula that's commonly used to help us do dilutions or calculate dilutions. And this is really the most common one, which is M1 V1 equals M2 V2. And that is sort of the ones are like before the dilution. The twos are usually after the dilution. The M's here are molarity. And the volume here is obviously volumes. M1 is usually the concentration of the more dilute, the more concentrated solution. V1 is how much of the more concentrated solution you need to use. M2 is your more dilute solution, usually the concentration. And V2 is usually your total volume of your new solution that's more dilute that you want to make. Now, earlier we talked about, and the other day we talked about that you should always use molarity. You should always use liters with molarity. But this is the one equation here, the dilution equation, where if you do want to leave it in milliliters, it will work out okay. So if you're specifically using this dilution equation, you really can leave it in milliliters. And the reason for that is if we were, for example, solving for, say, V2 in this case, that would be M1 V1 over M2. And if we put our units in, that would be molarity times milliliters divided by molarity. The molarities would cancel. And you would actually end up with milliliters on the back side of the calculation here. And even if you solve for M2, for example, which would be M1 V1 over V2, we put in the units, this would be molarity times milliliters divided by milliliters. The milliliters would cancel and you'll end up back with molarity at the end. So this is the one sort of formula where it really is okay if you want to leave the volume in milliliters, you can. If you are solving for a volume using this equation, you will get milliliters out. If you want to convert it to liters, it's perfectly fine. You would just get liters out as your volume. If you want to make sure you're doing it correct, convert it to liters, you don't have to worry about it. The real reason is, and I think we might have talked about this the other day, but when you actually do take milliliters times molarity, although molarity is known as moles per liter, it could also be known as millimoles per milliliter. So when you actually do that conversion here, you do not get moles, but you get what are known as millimoles, which is 1,000-fold different than moles. And again, if you come back and divide by milliliters, those two guys cancel and you're back to moles per liter, which is molarity. So the reason people always yell at you to convert it to liters, which is really the right thing to do, is because in most cases you're for moles and you're not looking for millimoles. So if you forget that that really is millimoles, if you use milliliters, you're going to be off by a factor of 1,000. So if you want to be safe, convert everything to liters and you'll always be probably correct for what you're trying to do the calculation. But you can definitely, in this specific situation, using this equation, you can leave the volumes in milliliters and it will work out okay at the end. Any questions on that there? Now, I would say most people use this equation M1 V1 equals M2 V2, but there is a more generic formula for dilution. And you'll sometimes see this formula, which is C1 V1 is equal to C2 V2. And the only difference is concentration. Concentration. What that means is, technically speaking, you could throw into here like percent mass to mass, like we did before, percent mass to volume to volume on both sides. You can really use any concentration unit you want in there, as long as they're both the same on either side. But since molarity really is the most common unit of concentration, Most people usually roll with the M1 V1 equals M2 V2, but as of recent years, a lot of books are rolling into C1 V1 equals C2 V2, so you might see them both. Any questions on that there? All right, so let's take a look at one here. Why don't you take a moment? And we want what volume of 19 molar sodium hydroxide is needed to make 1 liter of a 0.15 molar sodium hydroxide solution. All right, let's take a look here. So we're doing a dilution, and we know that because we basically have a more concentrated sodium hydroxide solution, and we want to make a less concentrated sodium hydroxide solution. So we do want to use our M1 V1 is equal to M2 V2. So we really can label all these guys, and it really doesn't matter, honestly, which one you make ones, just as long as you keep kind of the numbers that go together. So we'll go with the more concentrated guy as M1, so that'll be 19 molar. We obviously do not have a V1. We have a less concentrated M2, which is 0.15 molar. And we have, which by the way is 1,000 milliliters. All right, so we really could solve for V1 by dividing M1 to the other side. And that would get us V1 is equal to M2 V2 M1. Putting in our numbers here, we got 19 molar. We have our V2, which is, sorry, I wrote that backwards. I did that twice today. I want to see that. Hang on. All right. You think there's numbers, I would follow them. M2, so that would be 0.15 molar. That seems better. And 1 liter divided by our 19 molar. The molarities here will cancel, and that will get us 0.15 times 1, basically, divided by 19. Going to give us 0.0079 liters, as the units are liters, or approximately 7.9 milliliters of our sodium hydroxide. Any question on that calculation there? So basically what we have going on here is we do have a bottle of like 19 molar sodium hydroxide sitting there. We want to make a new container that is basically 1 liter or 1,000 milliliters and has a concentration of 0.15 molar. So this number that we just badly circled there is basically how much of the more concentrated sodium hydroxide we would take to put into our new container here of 7.9 milliliters of sodium hydroxide. Would I then top that off with like 1,000 milliliters of water, which is 1 liter? Would I want to dump like 1,000 milliliters of water in this thing? I actually would not, because what would my total volume be at that point? It'd be like 1,007 milliliters, right? Instead of 1,000 total milliliters, right? So a very common question that's oftentimes asked in dilution problems is actually a lot of times how you make the solution or how much water that you would need to add. So to figure out the water, typically it is the final volume, or V2, minus V1. So we really want to make 1 liter or 1,000 milliliters, which again is 1 liter. And we already put in there 7.9 milliliters of our solution. So really, if we take 1,000 divided by 7.9, it tells us that we need to put in there about 992.1 milliliters of water with it. So we would top this guy off with 992.1 milliliters of water. We would give it a nice mix, shake. And at that point, what we should be left with is now a total volume of 1,000 milliliters or 1 liter, and it should have a concentration point. Very common mistake that people sometimes make when they're making solutions is they go, oh, my total volume needs to be 1,000. So they put 1,000 in plus what they've already added. That gives you too much volume, obviously, at that point, which would change the concentration. When you use something like a volumetric flask, you don't have to worry about it because there's frankly a line you would go to, so you couldn't add too much. But you don't always make things in volumetric flasks. You could make them in beakers or other things. So sometimes that's a common mistake. Any questions on that there? All right, so let's try another one here. A calcium chloride solution, or not a calcium nitrate solution, and we want to know how much water is needed to make 500 milliliters of a 0.25 molar calcium nitrate solution if we start with a 5 molar solution. 5 molar calcium nitrate sitting there, which would be like our M1. We want to make a new sort of container there that's going to have a concentration of 0.25 molar, which would be like our M2. And it wants a total volume of 500 milliliters, which would be our V2. So it really is a dilution equation. So we are going to look for V1, which is really how much of that guy we need to take out. So using our M1, V1 is equal to M2, V2. Once again, here we're going to solve for V1. And that would give us that V1 is equal to M2, V2, M1. Putting in our numbers here, 0.25 molar. Once again here, it is okay to leave this in milliliters, but if you wanted to convert it to liters, it would be 0.5 liters. Once again, it's okay in this formula because here we will be dividing by 5 molar, which means the molarities will cancel. And we'll be back to milliliters. Obviously, if you converted it to liters, your answer would be in liters at this point. Either one's okay, unless it asks for a specific unit. 0.25 times 500 divided by 5 is going to give us 25 milliliters here. And obviously, if you were in liters, you would have 0.025. And this is 25 milliliters, though, of the calcium nitrate, right? So basically what we just calculated is we need to go into the more concentrated bottle and pull out 25 milliliters of it. But we are looking for how much water here. So this is a case where we can figure out the volume of the water by taking the total volume, which was 500 milliliters in this case, minus how much we already put in there, which was 25 milliliters. And that will get us something like 475 milliliters of water would need to be added. So we'll top this off with 475 milliliters of water. Again, give it a mix and a shake, and we should end up with a solution that has that concentration and that volume. Any questions on that now? So it's really important in dilution equation, dilution problems that you read the problem really carefully, because a lot of times people just kind of gloss over the how much water or how you make the solution, and they just roll into the equation. For V1, it typically is how much of the more concentrated solution you would use. And obviously, again, M1 would be the concentrated solution, and then our 2s would be our dilute solutions. Any question on dilutions? Okay, so the next thing we're going to then talk about in terms of solutions is actually stoichiometry. So we've done a couple of different types of stoichiometry up to this point. We've done sort of traditional stoichiometry, if you will, and basically taking grams to moles using the molar mass. We did some stoichiometry involving gases in the other chapter, and that is obviously doing the kind of the same steps, except we used the ideal gas law along the way somewhere. So solution stoichiometry, the good thing is it really is those same 4 basic steps, which is, you need to balance an equation, you need to convert to moles, you need to do the mole-to-mole relationship and convert those moles to some other unit. In addition, with solution stoichiometry and really any stoichiometry, even gas stoichiometry, you also could still have a limiting reagent sort of situation, which you would talked about before. A reminder that it is when each reactant. So either they're given to you the moles, or you have enough information to get to moles for each reactant. That is how you know it's a limited reagent problem. It can happen in solution stoichiometry for sure, and any stoichiometry sort of problem. So what is really the main difference? The main difference really happens usually in 2 spots. It happens here is how we get the moles. So instead of using grams to moles and the molar mass, here we use a lot of times molarity and solve for moles by taking liters times the molarity. Once again here, for sure, it has to be in as you're using the volume here. The other difference is also at the back end of the calculation. A lot of times on the back end of the calculation, we go from moles back to grams using molar mass. But very common when we're doing solution stoichiometry, sometimes we're interested in volumes, and sometimes you may actually be calculating the molarity on the back end. So a lot of times on the back end of the calculation, once again, we will use the molarity sort of formula there. So the middle part is, relatively the same. The stoichiometry parts are really the same, but we definitely will insert sort of molarity and volume and moles in those couple of spots. Any questions on that there? So let's take a look at one here together to kind of see how it goes. So we want to calculate the mass of sodium sulfate that must be added to 250 milliliters of a barium nitrate solution to precipitate all the barium ions and barium sulfate. Also calculate the barium sulfate this form. So we're going to just start with the first part of this, and we'll come back and do the second part here in just a second. So we're just going to really start with this first part, which is really we want the mass of how much solid sodium sulfate would be needed to react in this case. So it is a stoichiometry problem, which means in this case, we are not given the actual equation. So that is definitely where we want to start with in this case. So we're looking for the mass of sodium sulfate, and that should be Na2SO4 would be sodium sulfate. Sodium being +1, right? Sulfate being -2. So when we put it together, we get Na2SO4. That is needed to be added to barium nitrate. So that is barium nitrate, BaNO3 2. Again, nitrate being -1 and barium being +2. We should recognize this as what type of reaction here? This is a double displacement reaction, right? Positive, negative, which means positive guys are going to switch partners. So we're going to get this on the other side of the arrow. When we put it on the other side of the arrow, we want to just get the right formulas. So sodium is +1 and nitrate is -1, which means we should end up with NaNO3. Barium is +2, sulfate is -2. We should end up with BaSO4, which is our solid in this case. Any questions on getting those formulas there? Now that we have the correct formulas, and I super zoomed in, we also want to make sure that the equation is balanced, right? So it is not balanced in this case. So I think we do need to lay up a 2 there somewhere. And we would put a 2, it looks like, in the front of the sodium on this side. And I think that will take care of everybody there. Yeah. All right, so this is really step 1 of our stoichiometry problem, right? We got a balanced equation. Step number 2 is to take what they gave us and convert to moles. In this particular case, they told us that we had 250 milliliters of this guy, which is 0.2 molar, right? And actually, in this case, we are looking for how many grams of this guy. So clearly in this case, because we're looking for how many grams of the other reactant, and we don't have enough information to get the moles of both reactants, this is not a limiting reagent problem, right? This is just a basic stoichiometry problem, which means we can now basically go to convert to moles. This is the difference with solution stoichiometry. We're going to use the milliliters and the molarity to convert to moles, and that will allow us to get to moles using our molarity is equal to moles per liter. So let me get rid of that and we'll come up here and do it. Get rid of some of this here. Okay, so that's what we're going to do. We're going to use the volume and the molarity to get to moles. So our moles of barium nitrate would be, molarity is moles per liter, which means moles would be liters times molarity. So our 250 milliliters dividing by 1,000 or moving the decimal place, whichever way you like to do it, gives us 0.250 liters. And once again, my molarity, I'm going to pull out both units there so I can see it. And now I have everybody the way that I needed to do my calculation here. So we're going to take the volume, which is 0.25 liters, times it by the molarity of our barium nitrate, which is 0.2 moles per liter. The liters will cancel, and that will get us 0.25 times 0.2, 0.05 moles of barium nitrate. This is like step number 2 in our basic stoichiometry problem. Again, the difference here is we didn't use the molar mass to get to moles. We used the volume and the molarity to do so. Any questions on that there? The next step is to do the mole to mole relationships. So in the case of the first part of this problem, we're interested in this guy and this guy here. And from the equation, we could see it is a 1-to-1 relationship, which makes the math pretty easy here. We're going to do step number 3, which is 0.05 moles of barium nitrate. We're going to get rid of the barium nitrate because we don't want that. 1 mole of barium nitrate would give me 1 mole of sodium sulfate. The moles of barium nitrate cancel. 0.05 moles of sodium sulfate here. At this point, we actually are interested in grams of this guy based on the question. So like normal, we would need the molar mass of the sodium sulfate. And that would be 2 times 2299 for the sodium, plus 3207 for the sulfur, plus 4 times 16 for the 4 oxygens for the molar mass of this guy. And that gives me 2 times 2299 plus 3207 plus 4 times 16. That's about 142.1 grams per mole, 142.1 grams per mole. We will use that as our last little step here to get rid of moles and get to grams. So 142.1 grams per mole of sodium sulfate. Moles cancel and gets us about 7.1 grams of sodium sulfate would be needed in this case. And that really would be step number 4. So as you can see here, it really is still the same basic steps for stoichiometry. Slightly different here is obviously we use the molarity there and the volume to get the moles, but everything else is really the same. A variation of this is, and very common with what you do in titrations is, that step number 4, you would maybe use molarity on the back end or calculate the molarity. Again, that's sort of a variation on it. Any questions on those steps there? The second part of the question, I think that I wrote all over, want to know how much barium sulfate will we make. So part 2 of this question was basically how much of this guy would we produce? So we can basically answer that using some of the stuff that we did already. Since we already have the moles of barium nitrate, I can then go from moles of barium nitrate to moles of barium sulfate. So to do the second part of this question here, I'm going to start with the moles that we had here, since it's the same problem basically. So 0.05 moles of barium nitrate. Once again, at this point, we're going to do the relationship between barium nitrate for the second part and barium sulfate, which happens to also be a 1-to-1 relationship from the equation. So that's pretty good. 1 mole of barium sulfate from the equation gives us 1 mole of barium nitrate. That also gives us 0.05 moles of barium sulfate would be produced. That would be the theoretical yield of barium sulfate in moles, but we want grams, so we'll use the molar mass of barium sulfate. Barium is $1.37, I think, 137. So for barium sulfate, barium is 137.3 grams per mole. We got 3207 for our sulfur, and we also got our 4 times 16 there for our oxygen. So the molar mass of barium sulfate in this case, 137.3 plus 3207 plus 4 times 16, 233.4. So to figure this out, we would take our barium sulfate moles, times it by the molar mass here of 233.4 grams per mole from the periodic table. And that would tell us that we would end up with about 11.7 grams of barium sulfate, which would be our theoretical yield in grams in this case. So this kind of had 2 problems wrapped up into one, but they're all are still really the same 4 steps, even the second part. Equation, convert to moles, mole to mole relationship, and convert those moles to something else. So it's really the same 4 steps. Any questions on that there? All right, so let's take a look at maybe another one here. All right, we want to calculate the mass of calcium carbonate that forms when we mix 25 milliliters of 0.1 molar calcium nitrate with 20 milliliters of 0.15 molar sodium carbonate. And I think based on the time, this is a good stopping place, I think. Yeah. All right, any questions on